Apa lagi coba? Josie.
Very good morning to all.
కరెక్ట్ అయింది దీనికి ఇక్కడ
Very good morning to all. Today's chief guest and keynote speaker, Professor G. Sreenivasa Garu, Sciences, Saudi Arabia, and other dignitaries. A warm welcome to this second days of our international conference organized by our department on mechanical engineering and emerging technologies meet 2022. Friends, you are happily and comfortably enjoy the first day. So on this contest, I would like to thank to each and every authors. So effectively and efficiently deliver your speech, your papers. So now take the privilege, without wasting the time, I take the privilege to thank our today's chief guest Sreenivasa Garu and I say one more. It is my proud to say he is also my friend, and he also involved and attended one more program earlier 2 years or 3 years back in our college, and he delivered excellent lecture to our students. Sir, thank you, sir. Thank you for our cooperation towards our department and college. Continue the interaction with me. Thank you, sir. Now I request Abhishek so to introduce the today's chief guest and continue the further session.
Dr. Sreenivasa Gubba is a joint research scientist at KUST, Innovation and Clean Commercial Research Center of KUST. Dr. Gubba has 18 years of professional experience, comprising of 9 years at General Electric Global Research in Bangalore, and 9 years at various academic institutions in the UK, USA, and in India. Dr. Gubba received his B. Engineering degree in Mechanical Engineering from Andhra University, India in 2000, and MS by Research degree in Aerospace Engineering from Indian Institute of Technology, Madras in 2003. He received his PhD in Mechanical Engineering from Clockwork University, UK in 2009. His doctoral research involved development of a novel dynamic flame surface density model for turbulent prediction flame for large eddy simulation technique. Following the PhD, he worked as an EPSRC research fellow at Leeds University, UK, optimizing pulverized coal biomass flames for industrial power plants. Later, he worked as a lecturer in thermophysics at Manchester Metropolitan University, Manchester. Dr. Gubba handled conversion related projects related to gas turbines, IC engines, boilers, and gasifiers. Few technologies to name are PDHM, an IoT based solution for addressing boiler tube health, Dr. fuel injector for soot reduction in IC engines, and late wheel injectors for GE gas turbines. His current research's interests are in developing low emission commercial technologies, alternative fuels, and gasification. Dr. Gubba has 30 plus publications and 4 patents to his credit. We are all thanking you, sir, for considering our request for a keynote session amidst your busy schedule. We are happy and looking forward to learn from your session. Over to you, sir. Thank you.
Thank you, Abhishek. Thank you, Dr. Nancharaya. Thanks a lot to Bapatla Engineering College for providing me this opportunity. Just before going into the lecture, just I wanted to understand, am I audible to everybody?
Yes, yes. Okay, okay. It is audible.
Thank you. And you can see me as well, correct?
Yes, sir.
Perfect. Okay. Let me start sharing my screen. Can you just tell me, can you see my screen? Does somebody need to allow me to share the screen?
Srirav, it is given to the permission to you. You can share.
Perfect. Can you see my screen now?
Just it is connecting. Okay, connected.
Perfect. Okay.
Yes.
Before, yeah. So thanks a lot for the nice few words that Abhishek has spoken about me, and to all the students who are all listening today. Thanks a lot for providing me this opportunity one more time to deliver a lecture on some important issues, so that the whole idea is not to distribute the Gnan, but it is just to make aware of what we are doing, and at the same time to inspire you people so that you can choose appropriate career paths. So that's the whole idea. So the talk today, what I'm going to give is about a new energy vertical. But before going into the new energy vertical, let me just introduce myself from my end. I've been a research scientist right now with the Clean Combustion Research Center at KAUST. KAUST is King Abdullah University of Science and Technology. Been engaging in state-of-the-art research for the last 11 years or so. We have about 13 centers spanning across 4 different important pillars of the so like energy, food, water, and materials. Along with that, our management is looking for another two pillars, which are artificial intelligence and alternative energy. So these are the areas that just we are currently working, and basically very important for us to going forward. So the whole idea is not to introduce myself here, but just to give you what is cost, etc. I work as a part of like a innovation team as well as the Clean Combustion Research Center, so that my job is to translate the novel research to industry. So that means like I'm bridging the gap between the academia and industry in one way, and in second way, inculcate innovation culture among the students, so that they start thinking about novel things, and these novel things can be translated into products at the later point of time. So that's briefly about me and my role. Now let's come back to one of the very important area that just currently everybody across the globe they're talking about. So the title of the presentation is about ammonia and hydrogen, which is a new energy vertical. I have just picked up this image from a McKinsey report, which shows our world as a green and blue, which is representing current today's topic. So think about entire globe with so green and so bluish, and it's very attractive to see for us. But unfortunately, not every place is like the greenery or the bluish stuff. So there are plenty of other issues that just we are having every day, and some of the I would say like many of the issues are due to fossil fuels. But let me just take you into the presentation. Today, what I'll do, I'll try to pitch a story to you about carbon dioxide, which is known to us, all of us. And I wanted to talk to you about net zero emissions, what it means, net zero emissions, eFuels, what is this all fuss about the new energy vertical. And after I try to give you some research work that from our center, and I'll conclude the entire topic. So that is the agenda of the today's this particular delivery, the lecture. We all know that carbon dioxide is basically greenhouse gas, and the carbon dioxide has a lot of issues. It creates a lot of issues. But if I just take one step back, basically, how does this carbon dioxide is generating? So carbon dioxide is generating when you have hydrocarbons, which are your gasoline, diesel, methane, or any hydrocarbons, which are a combination of like a C and a H atoms, right? And when you burn them, typically, if you just put a methane equation, CH4 plus H2O, sorry, CH4 plus oxygen, which gives you H2O and carbon dioxide. On a complete combustion, you tend to see like water as well as carbon dioxide are supposed to evolve as a product. This is on a complete combustion. If it is not complete combustion, what happens is there will be some carbon monoxide, some nitrous oxides, etc. will deliver, and on top of it, you have your carbon dioxide and water as well. Now, the carbon dioxide, which emanates from this simple reaction that we just spoke about, comes out and it enters into the environment. Okay, what happens this environment when the carbon dioxide comes out? What happens to this? So typically, carbon dioxide, we don't really feel much about it. But what happens is over a period of time, when I say over a period of time, it may be 50 years, 100 years, or even more, because we've been practicing the, like the way how we are doing the stuff, combusting biomass or combusting fuels and just leaving emissions to rest of the world. So it's been over a period of time. And this over a period of time, what happens is a lot of issues. So, for example, I highlighted some of the issues, whatever you see here. So it can start shrinking your water supplies. So there are a lot of geographical changes and changes in the weather patterns, which we all see, and there is a rise in temperature. I'm not too sure you're in the midsummer in Andhra right now, and over a year and a year, so you see like the soaring of the temperature. So without AC or without some sort of like conditioning methods, we were unable to stay indoors. It's very difficult for us. So, and we also see like the summers and winters, so they come and just go as they wish. It's not as per like the observations of our previous generations. So uh, it also changes the supply of the food. And there are a lot of acid rains. So what is acid rains? Basically, if you have some sulfur compounds in rain, so that's really bad. That is what is called acid rain. And finally, and for most things, is increasing the sea levels. Okay, you may think, okay, hey, like increasing sea levels, what does it impact? So there is a huge impact of it because the available land for us to evolve as a human species tend to reduce. Therefore, there will be more war for real estate. Means, okay, I wanted to live on some place, but there's no place for all those 8 billion people on the earth. And of course, it's not just for living. It is, you wanted to do agriculture and production, etc., etc. So there are a lot of issues and pretty much complicated problem. And if you think for all these problems, there's only one thing which is causing, like increasing the CO2 in the environment. Then we wanted to understand, okay, how do we reduce CO2? Right? I'll come to that piece of information. But if you just see on the right hand side of my chart, it's very interestingly mentioned about if I just have a kilogram of CO2 and on the earth, from where the CO2 is coming from. So you see like building operations and building materials and constructions is roughly about 40%, right? And then industry, and you name all the industries, it may be pharmaceutical, mechanical, manufacturing, small scale, large scale, everything put together, it's about 32%. And the transportation is about 23%. You put together like four-wheel transportation, two-wheel transportation, or trains, or you call them, like whatever it is, right? Everything is put together about 23%, and 6% is from others. Basically, this others is the way how we live, and of course, we all emit carbon dioxide, right? So we eat food, and when we eat food, so the digestion happens in our stomach, and there is a carbon dioxide releases out from us. So the 6% is from us, let's put that way. Okay, maybe it's a way of living or way of eating or whatever it is. Now, put together all these things, the 100% of the carbon dioxide is causing a lot of issues on the environment. How do we reduce it? That's a very important factor, but just let's go into one level deeper onto the numbers so that just we understand where exactly the problem lies and where is the problem before we discuss about the solution. So I try to put a chart from Statista here, which talks about annual CO2 emissions across the globe between 1940 to 2020. So the scale is in the billions of metric tons. And you see like at 1940, okay, let me just use my laser pointer. So if you just see like a 1940s time frame to 2020 time frame, 1940s, that's, for example, roughly before our independence, so the emissions were about 5 billion metric tons across the globe. Now today we have about 39 or 36 metric tons, billion metric tons in the current scenario. It's always increasing. because of whatever you call like a life sophistication or industrialization, or because of wars or development, whatever the so-called development as we call. So it's keep on increasing. And if you just put together a weather chart, again a state, which I have not done here, but it would be very interesting to see like how is the global warming. And many scientists do confirm that the global warming is due to the carbon dioxide. And we can evidently see that it's increasing, and the increase is not like a linear, it is non-linear, right? It's non-linear. Basically you can just fit a polynomial to it, and it's very a complicated equation anyway. Now there are two scenarios that just we need to talk about. So the two scenarios are 2008 and 2019. If you just see these two scenarios where I have rounded up here, in 2008, because of the global recession, so there is a dip in the CO2 emissions because people has no money, so people do not travel, or people do not have much to spend, or people don't want to do whatever it is, therefore there is a dip in CO2. Similarly, in 2019 or 20 time frame, we all know there was a pandemic, which is a COVID-19, has made all our lives miserable. If it is not miserable, we would all meet in a physical sense. But today we are just meeting online because of COVID and travel restrictions, lockdown, etc., etc. Still, we are having some issues. But at the beginning of the 2019, where all the countries were taking serious measures about COVID, you see like a huge dip in the CO2. And of course, this is not new to us, because all the newspapers, global news were talking about our electricity consumption, and people were debating COVID was making good or bad, or in which sense, etc. So anyway, so that's keeping that aside. The key point here is our behavior is able to give us huge trends on the CO2 emissions, which are released year on year. And of course, so as I was telling you, if you go easy and light on the environment, there is an opportunity to decrease it. But I don't know, like what happens in next few years or whatever it is. So now let's see now. Okay, I think just I wanted to highlight here. Now it is between developing and developed countries, or third nations they call. Now people are fussing about saying, hey, look, so you people are causing the trouble. It's not us. Now each country is blaming everybody on these COP meetings, or weather meetings, or climate change meetings, wherever they meet. And now if you just go slightly deeper into the data, now what you see here is the data available from 1750 to 2020. Very interesting chart. So the blue is all talking about the Europe. So if you just see this blue, so during 1750s, entire CO2 emissions are from the European region. And if you can remember your history, whatever you studied before your 10th class, you can put together all this information due to the industrial revolution in the Europe, and due to the lot of wars that were happening in Europe. So basically Europe was on skyrocketing speed in the industrial revolution. You name it, like a sports, or you name it all the warfare, or you name it like a ships, or you name it like guns, or whatever it is. Europe was is basically leading in the particular area, and then is followed by EU 27 countries. So basically, and then what happens is, this is the USA. So USA picked up a little late, and when USA picked up, okay, USA was growing, as well as by 1880s, etc. Now, if you just see by 1880s or in 1900, the rest of the globe is really a tiny percent. It's roughly about 1 or 2%. Now, if you just see, these colors are growing and they are expanding. If you just carefully notice what are all these countries or what are all these regions. For example, China and India. So, of course, China is the sky blue, where a significant amount currently about 17%, I believe, and India roughly about 2% or 3% in India in 2020. But rest of the Asia is again a significant amount. If you just consider the entire Asian continent, so India and China are put together is equals to the rest of the Asian countries. CO2 emissions currently. Now, I mean, if you don't talk about the past, if you talk about the present, irrespective of what happened in the past, what we see these numbers are definitely alarming, and definitely our contribution, China and India, and of course the rest of the Asia has to work on it. Of course, we need to work in the EU 27, and the USA, other countries as well. So these, what do you call, like CO2 emissions are not so small. So just to give you another perspective, I wanted to dive into per capita CO2 emissions, because that will tell us, hey, look, Indians are 1.4 billions and Chinese are 1.5 billions, and entire center of gravity is put together into the entire Asian countries. So, and entire, if you just see that the population is about 8 billion, and out of 8 billion, roughly about 30% or 35% of the population is in Asia, right? When you just do that balance, load balance, then you see, look, Asia is generating less CO2 compared to USA and other stuff. So let's talk about some numbers. Now, this is again per capita CO2 emissions in 2020, okay, by country wise. So if you just see Qatar, which is one of the Asian country, is topping with roughly about 37 metric tons per person, and so on and so forth. You can see like we are going down, going down, going down, and of course China is a 7.41, so which will be somewhere here before Iraq, Hungary, or somewhere this particular place, because this has about 200 countries. Some of the countries has been skipped by the plot, but still we have like India 1.77%, which is somewhere here in this region, and China somewhere in this region. So I mean, we may say like India is 1.77%. We don't need to really worry about it. But if you just look at the history, which I did not put here again, we've been westernizing a lot. Because of the westernization, we people are using the gasoline or diesel, or you name it, like it's a sophistication of our life, or you may call it as the westernization of our life, whatever it is. Our per capita CO2 emissions are increasing alarmingly. Again, if you just take just India definitely has exponential growth in CO2 emissions. Nevertheless, we are not bad compared to any other developed nation or any other places in the world. But if you just think about ourselves, our environment is getting bad, and therefore, irrespective of like blaming somebody else, we need to take some action on it. Anyway, so this is all the brief history about the CO2 emissions, just to tell you the importance of like a CO2 on our weather. Therefore, you appreciate the subsequent message what I'm going to deliver today. Now let's consider about a net zero emission. What actually this net zero emission is? If you see, I gave you a very simple equation of like a fuel plus oxygen or fuel plus air gives you CO2 plus H2. Now the CO2 which is produced from this particular reaction, can I balance it out? If I can balance it out, how do I balance it out? So this is what it is called a net zero emissions. Means I read out here, which is I've just captured from the climate concept. Net zero emissions refers to achieving an overall balance between the greenhouse gas emissions produced and greenhouse gas emissions are taken out of the atmosphere. So we know that it's inevitable to burn some fuel, right, for our living. When we burn this fuel, CO2 generates. Can I take out the CO2 from this particular reaction? If I can, how do I do that? Or if I cannot do that, can I take it from the environment in some other ways? So basically, it's just simply balancing it out like your credit and debit on your bank account, right? So you wanted to put something and you wanted to take out something. So basically, if you just maintain a net zero account or net zero emissions, that means you put something into the environment, you take it out of it, therefore it becomes zero, right? Right now we have a lot of CO2 deposits, like CO2 credits. We wanted to take them out. That's the whole balance of the net zero emissions. Now, I also put something from a McKinsey report, the below. So they have evaluated all the entire scenarios. It's a very comprehensive report. The comprehensive report shows that there are 7 areas like energy, land use system for the global emissions. Okay, these areas are like a power, industry, mobility, buildings, agriculture, and forestry, and other land uses. It might be use of for recreation, used by us, etc. And finally, waste management. So these are the areas that just we need to consider majorly to capture the CO2, right? Okay. Now there are 2 things here. Capturing CO2 after you release it, yes, that's one way of doing it. Or you don't want to really release the CO2, that's another way of doing it. Or can I use some sort of like a fuels which are completely carbon neutral from the beginning itself, right? So this is the ideology behind it. Now let's talk about this in detail. For example, I just wanted to give you a concept of like a green fuel or a eFuel, and I'll also delve into the concept a little more here. So for example, if you just see your green fuel or eFuel, what actually a fuel is, I discussed about in the beginning of this presentation, your fuels are simply a combination of the C atoms and H atoms, like a CH4 or C2H6, or like a methane, propane, ethane, etc., or your gasolines or diesel or the C17H16s, etc. So basically, there are higher hydrocarbons which we typically study in organic chemistry, isn't it? Now, if you just see what currently I am doing is I am deriving these fuels from a crude oil which has been evacuated from the earth. Instead of using these fossil fuels or the so-called fossil fuels, can I get my CR10 from atmosphere? Okay, there is a lot of carbon dioxide available in air currently. Can I just use some sort of a process so that I grab the CO2? Or else, okay, you grab the CO2 from the flue gases of a furnace or from industry. So that's why just you get your C atom. And you need a H atom. The H atom, let's say, for example, you wanted to use water, and we have abundant water. Okay, for example, I talk about the sea. Sea has a lot of water, and you take a H atom from the sea. So how do I get the H atom? You need to split your H2O. I mean, how do I split it? I need to provide some electricity, right, through electrolyzer. And how do I provide the electricity? So let's use the renewable resources, such as like a wind or a solar. And when I use these 2 things, due to the electrolysis, I can release the H atom. Now combine this H atom and a C atom so that just you can make a different hydrocarbon, which you can put together in any of, for example, for transportation or for industry, anything, you name it. Now, the process called in between combining this C atom and H atom has been invented back in 1800s, which is called a Fischer-Tropsch process, which is very standard process which currently we use it. So these processes are already very readily available to us. Okay, so basically, if I produce a fuel, right, from electrical or renewable resources, that is what I call e-fuel or the green fuel. Now, if you are into this particular topic, you may hear like blue, gray, green, etc. What are these colors associated? I just wanted to give you something. Okay, before going there, I just wanted to tell you. Now you're all talking about the C and combination of the H. Can we make sure that these are all burning in our current engines? Because you change the way how you're getting fuel from your petrol pump or fuel station. Does that mean like my existing infrastructure works or not? That is an important question to be asked, because I cannot really change the existing infrastructure immediately. Over a time period, yes, I can do that, but right now I cannot do it. So if you just look at the energy densities, because energy densities are very, very important. So for example, in your bike or a car, instead of like a gasoline or a diesel, and if you wanted to put something like ethanol, methanol, etc., they may not work because of various reasons. One of it is the energy density. Okay, let's see what I wanted to give you a more perspective on this. If you just see the energy density, which is written in the kilowatt hours per liter. For example, what I do is my current fuels just we use petrol, diesel, and kerosene. They are roughly about in between 9 to 11 kilowatt hours per liter. I mean, so like, okay, I fill a petrol tank and I know like how many kilometers I can go. Whereas on the far left hand side, you see a lithium ion battery. You like a 0 point or maybe right. So that's why we're all working. We know like currently e-vehicles in the market, but e-vehicles are not as good as the current vehicles because of the energy densities. Of course, people are claiming like a 200 kilometers per single discharge, 400 kilometers per single discharge for a single charge. Of course, there are plenty of issues that just we tend to see today, right? So there is a lot of research going on to make them better and better. And there will be a day that just the lithium-ion battery on this scale just moves somewhere here. So no doubt about it. But if you just look into the other fuels like the hydrogen, CNG, methanol, bioethanol, autogas, etc., they have different sorts of like energy densities. And we wanted to talk about the CNG as well, because we see CNG in our automobile sector. People might have experienced this. They need to keep on changing this CNG cylinders, etc. Right? So the energy density is a very important factor when we consider, hey, look, I can combine the C and H atom and then just make my fuel. Yeah, it's a good idea, but just can we be there or can we be there at the same place? So the ideology is, yes, we can be there, which, for example, hydrogen and ammonia, which my current topic are. So the hydrogen is somewhere here and ammonia will be somewhere in between. But on the other hand, you need to consider the flame speeds as well, because the flame speeds are very sluggish by ammonia and flame speeds are really fast with the hydrogen. In order to get the same amount of the pressure or same amount of the reaction rate, this is very important, very, very important. Anyway, keeping that aside, now if you just say by the concept of like e-fuels or green fuels, how does the forecast looks like from 2025 to 2050? Again, all these things are possible with two things. One is government policies, and the other one is awareness. So government can make a policy, but if humans or unaware of these facts, it's impossible to bring the changes. So, as all individuals, we have to follow, and at the same time, government should impose certain sort of like benefits or penalties for not using them. Anyway, keeping that aside, because that's not the forum here. Now you talk about 2025. What happens is there is an approximate use of like a 4% of the eFuels because of the current outward looking. So these eFuels currently based on the EU price, they cost anywhere about 1.61 to 1.99 euros per liter, right? So that's a lot right now. But just going forward, you see like 2025 to 2050, it's possible that we can be able to replace fossil fuels with the green fuels, 100% green fuels. And by then, by 2050, so you may see like a decrease in a significant decrease in the price per liter of green fuel. So the definitely it is possible to bring down the prices, and at the same time to bring up the availability of these green fuels. So now we talked about the green fuels used in our existing infrastructure, and the cost as well, and the policy as well. Now what is left? So everything appears to be very interesting, right? Now let's talk about what is the energy vertical. If we talk about the hydrogen cannot be transported in the easiest way like the gasoline or diesel is being transported. Therefore, what we need to think about is we need to think about a carrier. So it's completely you notice that there is a good potential, but this good potential has a certain challenges. So some of these certain challenges are either it has to be a totally new fuel to reach equivalent of like a petrol, gasoline, or kerosene, which is being used by the current market, or else a fuel from an existing process that can replace entire fuel chain. Now, if you see the ambitious pictorial representation from 2025 to 2050, it appears okay. If I wanted to go with the completely new fuel, it is impossible to achieve these targets by 2050. So therefore, it's ideal if I can use a fuel from an existing process that can replace the entire fuel chain. That's amazing, isn't it? Now I wanted to bring out ammonia. We all know ammonia for decades, but let's talk about the transportation sector. The transportation sector is emitting about 23%, and if transportation sector can inculcate ammonia, industry sector can inculcate ammonia very quickly. That's keeping that aside, how they inculcate. But just let's look about the ammonia, the facts about ammonia. Ammonia, it's simply the chemical name of it is NH3. And whenever I talk about ammonia, perhaps all of you in Andhra, you might be able to realize that ammonia will be used as a fertilizers in our fertilizers, and which is not new to us, isn't it? So the ammonia as a gas has been used in 1940s in this bus. Okay, they used ammonia and the coal, gas basically, and they ran about 100,000 miles successfully in 1940s. And in 1960s, the US Army used a rocket plane X-15, which has been powered by ammonia. So it has been used, and all the records has been set by the US Army on that. And 2007-2012, Michigan University, they had a gasoline dual fuel vehicle, which has been working very nicely. They tested it, and they tested for 3,800 kilometers. And 2012, 2015, KIEA, that's a Korean Institute of Energy Research, ammonia gasoline dual fuel. So they made about 10 liters, 100 kilometers per given 10 liters, which is not nice as per the Indian standards right now. So that means like you have to have a huge fuel tank, right? Isn't it? But however, people are working on bringing this up to a little later stage. But if ammonia is cheaper, I would not really bother to refill it, and I would not really bother if there is a fueling station, right? So just keeping that aside, I think scientists are working on it. So it appears like ammonia is the best contender. Now, if you just see ammonia, this has ammonia, and this has a nitrogen as well as the hydrogen. I will talk about a little bit of chemistry as well in the subsequent slides. So if I wanted to use hydrogen, yes, I can use it, or I can use it ammonia as it is. So I think this is why ammonia is being considered as a very good new energy vertical. I just wanted to highlight, it's not like ammonia is new to us. Currently, we are producing huge quantities of ammonia. Of course, 70% of it goes for the fertilizers. Fertilizers, that means like in agriculture. So ammonia, we know how to produce, and it's a very standard process. It has been used for ages. For example, if you just see here, China, Russia, United States are in the first 3 ranks, and India being the 4th one. So we also has a very good ammonia infrastructure in our country. And of course, China, they are the highest producers. Of course, we import from China as well, and we import from somewhere else as well. So anyway, just keeping that aside, it is well known across the globe. Across the globe, they know that how to manufacture, how to produce NH3, and at the same time, how to transport NH3 from one place to other place. And there is an existing infrastructure, better fuel than ammonia to replace this entire infrastructure. Now you may ask me a question, sir, like you said about ammonia, all well, but ammonia is being produced currently differently, right? So it's not produced by the renewable resources. So that is the logic here. So now I know, like, there is two different pieces of the problem. One problem is we have identified air fuel which can replace, and we have identified a method so that we can get the green fuel as well, correct? Now let's combine these two things. Now, if I combine these two things, what I understand is my hydrogen and nitrogen, which is in ammonia like an H3, can I grab these two elements in a sustainable way? For example, let's talk about the hydrogen. The hydrogen can be brought from the water. I use the seawater desalination. I can use the water split, and I'm using the electrolysis, and I get the hydrogen atoms, right? And of course, I use for all this entire process renewable energy resources. And nitrogen, how do I get nitrogen? So air separation units. So if you go to your petrol filling stations, there might be air filling station for your tires. So if you notice carefully, now people are using nitrogen in your tires as well. So how do they get the nitrogen? They get the nitrogen through an air separation unit. From the air which is available to us in the abundant portion, they simply capture the nitrogen, and then just they fill the nitrogen into your tires. Okay, so nitrogen has a different advantages. Let's keeping that aside. Now you combine this hydrogen and nitrogen, which is all known to us. But what is important is this bit here. All I wanted to do, all this is through renewable energy resources. Okay, now use a process called Haber-Bosch process, and you can generate a green ammonia. So this rest of the bottom chain is all known to us, and only this is what it is challenging, and people are trying to achieve it. Again, to go to green, I mean, of course, I used a different slide here, green hydrogen, blue hydrogen, but they are not different. You can simply replace it a green hydrogen or ammonia, or a blue hydrogen or ammonia, green hydrogen or ammonia. Anything, the processes are all same here, but I wanted to highlight why the color associated with the blue, gray, or green. And we talked about the green. Green is fully from the renewable energy resources. And to achieve complete green, tomorrow it's very difficult, but going forward, yes, it is possible. But in the interim, what we can do is we have different colors associated, like a blue and gray. What is gray and what is blue? So gray is the existing processes, means now the current processes use fossil fuels or natural gases or water to get the H2. Okay. Now this CO2 is being emitted to the atmosphere. Okay, which is the current state of affairs. Like today, whatever we are doing. If, for example, whatever the ammonia or hydrogen we are producing, this is called a gray hydrogen or gray ammonia, which is current. Means, okay, now the blue, what blue is, now I am just generating the CO2 and capture the CO2 in a container or capture the CO2 somehow, maybe amine techniques or cryogenic techniques, etc. Then this is called blue hydrogen, because you are actually emitting CO2 but capturing it. Whereas in the green fuels, you are not emitting any CO2 at all in the first place. So therefore, the green is very attractive. And of course, we cannot really go or jump into the green. We need to go step by step, like a blue and a gray. So that's what the different colors are associated with this. I kind of like skip this, but just very briefly. Now, if you just look into the production, so there are many elements which are involved. We need to grow our renewable resources as well. And there are other problems associated. We know about ammonia transportation, no doubt about it, but going forward, you need to have more ships or more pipelines or more transportation devices, and therefore you have to increase it. So there is a bigger chain or bigger chain of opportunities that just they come as soon as there is something new comes, right? And of course, the utilization. So utilization means like hydrogen can be utilized in fuel cells, or ammonia can be utilized in the combustors as it is, or you can crack them. So there is an intermediate technology like a cracking, etc. So there are other end of technology at the utilization as well, which comes into the picture. Now, a big question is renewable energy resources. And we talked about the renewable energy resources, solar and wind, and where are we on that right now? If I don't talk about this, it's not appropriate. So currently, this is the PV power potential on the globe. If you just see, the red indicates the highest kilowatt power, watt hours per kilowatt power. The blue indicates the lowest here. Now you can see like very few regions in countries like China and northern parts, they are kind of like a blue, but majority of